Hi guys, in the last couple of days I've tried to figure out how to improve the power output of my wind turbine. Originally I had only used this LM2596 converter, which will convert the input voltage to the set output voltage, and the set output voltage is regulated by this potentiometer, and I've regulated it to 5 volts. The input voltage needs to be at least 1.5 volts higher than the output voltage. Now, the problem was that the stepper motor seemed to produce only around up to 4 volts. Anyway, I then had to think of something that increases the voltage at the input side, and I used these two converters, which will convert an input voltage between 2.5 and 5 volts to a set output voltage. In this case that was 12 volts, and as it had turned out later, the stepper motor can produce up to around 20 volts at rotation speeds of 1000 RPM, and that was far too much for these converters. What they do then is they just channel through the whole voltage and the whole power to this module, but the overall power output by this module is only about 2 watts. That is 400 milliamps, cannot be surpassed, no matter how fast the wind turbine rotates. And so I then left this one out and only used these two to check the power output if I used only them. The power output then becomes higher though. I've measured it up to 13 volts times 280 milliamps, so somewhere around 3.5 to 4 watts. And unfortunately that voltage has hardly any use for me, because I at the most time use USB devices or charger modules for lithium-ion batteries, so they couldn't be really used just on their own. And then I came across another module, this one, which is a step up, step down converter. That is, it can convert the input voltage to a set value, in this case 5 volts, as can be seen there. And it doesn't matter if it's high or lower than 5 volts. It always produces 5 volts at the output side if the power input, of course, is enough, if the amperage is also high enough. Unfortunately, it has a disadvantage, and the disadvantage is that at high rotation speeds the input voltage surpasses 16 volts, and that's the limit that this module can bear. And above 16 volts it will block, and the output voltage will only reach 1.5 volts. But it's still the best choice, because this only happens at very high speeds, say at 1000 to 1200 RPMs of the wind turbine, and such speeds usually won't be reached in your average storm, so I think it's really the best choice. This alone did increase the output, but not very much, and later in the video you will see that I've made a couple of changes. At first I exchanged the motor. The NEMA 17 was replaced by a Mitsumi stepper motor, and I've also added a couple of capacitors, which reduce the reactive power that's coming from the stepper motor, and by that increase its power output. That's the power that's available for usage. And so these improvements have really increased the power output quite a bit. But more on all that in the video. So I've decided to replace the NEMA 17 stepper motor by this beauty here, a Mitsumi M49SP3K with 4.8 ohms, because it has a much more stable output. That is, it doesn't jump to very high voltages like the NEMA 17 at higher RPMs. For example, NEMA 17 jumps to about 20 volts when reaching 1200 RPMs, while this one only reaches hardly 9 volts, and therefore it's much more suitable for the converter. I just hope that this adapter for the shafts will fit, because I've made this myself, while this one I have bought. This is around 9 millimeters on one side for the motor and 8 millimeters again for the shaft of the wind turbine. Okay, now it's inside, everything fits together. Let's hope that the wind will overcome the torque of this motor. I have no idea if it's bigger or smaller. It feels like that it's a little bit smaller than the torque of the other stepper motor, but to further increase the power output of the stepper motor, I have now added a couple of capacitors. For each coil, a pair of 100 microfarads, 50 volts capacitors. So each side receives around 50 microfarads, because they are in series, and they are anti-serial, that is, their terminals are plus together, and minus are connected to the cables of the coils of the stepper motor to prevent their damage because of the alternating current. The current might otherwise be on the, for each half wave, on the wrong terminals, and that would destroy them. So they have to be set in anti-serial order. Now these values seem to be the best ones that I've tried at relatively high rotation speeds of the rotor, and I've tried some higher values and some lower values, and with these the voltage reaches about 3.7 volts at quite fast rotation speed of the hand drilling machine, but not the fastest rotation speeds. When at a certain speed of the hand drill, or at a certain RPM, the voltage will drop from 3.7 to around 1.5 volts. That's because of this converter, which only can input voltage of a maximum of 16 volts, and the stepper motor in combination with these capacitors obviously produces a voltage that's higher than that, and therefore the converter will shut down in a way that the voltage decreases to around 1.5 volts. So I think that's a good compromise, because the wind speeds won't probably reach such high RPM all the time. I'll now make the test with this hand drilling machine and the load of 4.6 ohms there, and I will slowly increase the RPMs, and at a certain point the voltage will reach around 3.5 to 3.7 volts, and after that, with the RPM increases furthermore, the voltage will drop to 1.5 volts because of the converter, which only can input around 16 volts. Let's see which value we can get. Okay, let's try. That was around 3.5 volts. Let's see if we can go a bit higher. Alright, as you could see, for a brief moment it was even at around 3.7 volts. At the first test I had no such difficulties to reach 3.7 volts. Maybe that was because all components were temperature wise relatively cold, and I've used them quite a bit now, so when I've warmed up that the voltage doesn't increase that much anymore, but 3.5 volts can be reached definitely. To get 5 volts at the output, there has to be a load of at least around 10 ohms at the highest speed of the hand wheel, which is at about 1000 to 1200 RPM. It's more realistic to assume something like 400 RPM in your average storm, so the load will probably be better if it's at least 20, maybe even 30 ohms. So at 5 volts you should use only devices that have that kind of resistance. So let's test this, which voltage we reach with this resistor, a 10 ohm resistor, and the hand wheel at the maximum speed. It is at around 1200 RPM. So there we go, we had 4.92 volts. Now let's see what we can achieve with this USB meter here and a 47 ohms resistor attached to it. First go at low speeds and then increase the speed furthermore. As you could see, at relatively slow speeds of the hand wheel, the USB meter turns on and shows a value of 5 volts at the input and amperage of around 100 milliamps, as it should be with a 47 ohms resistor. And if I increase the speed even more, the voltage doesn't drop any. So the results are as follows. We can achieve a power output of around 2.8 watts at a certain RPM, not the highest RPM of the hand wheel. So the previous record was 2.3 watts without the compensation capacitors at the highest speed of the hand wheel, so that was quite a bit of improvement. And with using a 10 ohms resistor, we reach 4.95 volts at the highest rotation speed of the hand wheel, and with 47 ohms we can reach also 5 volts at rather slow rotation speeds, and even with a USB meter in between. So this wind turbine can be used for charging batteries and for using some USB devices with relatively low power consumption. Okay, that's about it. I hope you liked the video. If you did, please give a thumbs up, maybe even a subscribe, and if you feel like having something to say, then leave a comment. Okay, until next time, bye.